What's up, guys and girls? Welcome to AP Statistics. In this video, we're going to talk about probability of multiple events. A lot going on here. We're going to combine lots of different things that we've talked about all unit long for probability. So lots of good problems. Let's dive right in. So what is this video all about? Well, in the previous lesson, we discussed the probability of an outcome in a single chance event, like selecting a marble at random. Hey, what's the probability to get a blue marble? Well, in this lesson, we're going to discuss the probability of an outcome across multiple chance events, or one chance event repeated. Let me give you two examples. So select a marble at random and then spin a spinner. So we got two completely different chance events, selecting a marble, spinning a spinner, and we want to find the probability of getting a blue marble and landing on the number 2. So we're literally doing two chance events at the same time. Or again, as I said, maybe one chance event repeated. So select two marbles, one after the next. What is the probability both are blue? So I'm not just selecting one, right? I'm selecting a second. So I'm doing a chance event, selecting a marble, and then I'm literally doing it again, selecting another marble. All right, so one more thing to note before we kind of dive in here is that there is a difference in how we use the word and, right? There's kind of two ways we could use the word and. So we could select one person at random who has blue eyes and black hair. So that's one person that has two characteristics. And to talk about that, we're going to use the word and, right? Blue eyes and black, right? We talked about that. But a second way we could use the word and is this. Select a person who has blue eyes and then select another person who has blue eyes. So in this case, I'm still using the word and, but notice I'm kind of saying and then. So I'm referencing the fact that I'm going to do one random event, select a person, hopefully they have blue eyes, and then I'm going to select a second person. So, and then I'm selecting, I'm repeating, or I'm doing another chance event. Whereas if we talk about a person or an object having two characteristics, that's what we just say and. Blue eyes and black hair. One person has both. So you got to really make sure you understand the use of the word and, because it really does matter when we start talking about probability. All right, so let's recap, because the addition rule, I know you say, well, this is the addition rule, right? But this is a rule that's used through all probability. So let's make sure we understand the addition rule. Very simple. It says if you're trying to find the probability of A or B, event A or event B occurring, you take the probability of A, add the probability of B, and you subtract the probability of A and B. Said it again. I've said it before. I'll say it again. I'm not getting rid of the A and B. I'm preventing it from being counted twice. Because if there is overlap, some of this probability of A also contains B. Some of this probability of B also contains A. So the A and B is kind of embedded in each of these values, so I just don't want it to count twice. Now, the other thing that I want to make sure I say again is that the opposite of A or B is neither. No A, no B. So if you think about it, the statement A or B is A or B or both. So a lot of kids think, well, then why are you subtracting? Again, hopefully you understand, I'm not subtracting to get rid of it. I'm subtracting it from being counted twice. Okay, pretty simple, pretty basic. But don't forget about that mutually exclusive. Mutually exclusive means that A and B is impossible. So if you are mutually exclusive, and only if you're mutually exclusive, this is a big, beautiful zero, which means you don't have to worry about it at all. But it's always important to consider, is there any overlap? Because if there is, you need to subtract it. All right, we also learned about the conditional probability rule. Very simple rule. To find the probability of A on the condition of B, in the numerator, you find the probability of A and B. And the denominator, you find the probability of B. Divide, you're going to get your answer. Now, I do want to briefly show something right here real quick, right? We are allowed to do algebra. If we take the probability of B and multiply it to the other side, we get the probability of B times the probability of A given B equals the probability of A and B. So you can find the probability of A and B with this formula right here. But you got to be very, very careful when you're multiplying, because you're only allowed to multiply probabilities if you consider the fact that B has affected A, which is, of course, conditional probability. That may seem a little bit confusing, but once we start diving into examples, I think you'll understand it. All right, and one more kind of main idea here. This is really simple. I want to try to make this as simple as possible. If you are finding the probability of multiple outcomes, I need this to happen, and then this, and then this, and then this, and then this. Simply multiply the probabilities of those outcomes. It's that simple. But that does come with a twist. You can multiply probabilities together as long as you consider if the probability of the second outcome is impacted by the occurrence of the first outcome. And again, that's just thinking conditionally and independently, right? Or non-independently, I guess I should say, because if B affects A, then you just got to be careful when you start multiplying. So every time you start multiplying probabilities, just consider, do I need to change what happens second because of what happened first? Or do I need to change what happens third because of what happens second? It's not difficult to do this. You just have to consider this in your brain. And that's what I'm going to teach you through a series of examples right now. So here is the big formula for the probability of A and B. It's actually similar to what I was talking about earlier when I showed you how you could take the conditional probability formula and just do a little multiplication. But again, here it is. The probability of A and then B. So if I'm looking for the probability of A to happen, I want A to occur, and then I also want B to occur, you simply take the probability of A and you multiply it by the probability of B. But again, you have to take into account, did the occurrence of A affect B, which is, of course, conditional probability. So at the end of the day, I am multiplying A times B. Probability of A times the probability of B. But because B comes second, I have to consider if A affected B, which means that they're not independent. If A affects B, they're not independent. So it is important to know that if A and B are independent, right? Remember what that means. Independence means that the probability of A equals the probability of A given B. Or I could say the probability of B equals the probability of B given A. It's the same thing. Remember, whoever goes first has to still go first on the other side. So if we are independent, to find the probability of A and B, you just simply take the probability of A times the probability of B. If you are independent. Because if they're independent, then you don't have to worry about it. B doesn't affect A doesn't affect B, multiply away. But if they are not independent, which I'll be honest is often the case, all you have to do is consider the fact what's happening second is impacted by what happens first. And I know we haven't done any examples, but we're about to in 1 second. And all I'm asking is that you just process and think about this as you're solving the problems, and it's actually quite easy. All right, let's dive into an example with 2 independent events. You flip a coin and you spin a spinner. Why are those independent events? Because the coin doesn't care what the spinner does, and the spinner doesn't care what the coin does. It's not like the spinner has a brain that says, oh, there was a head, I guess I'm not going to spin for this number, right? Or the coin's not going to sit there and say, okay, let me wait and see what the spinner does, and then I will determine if I'm going to be a head or tail. They're completely independent events. What happens on the coin has no bearing on what happens on the spinner, and vice versa. This makes multiplication pretty easy. So the coin has 2 sides, tails and heads. The spinner has 7 sections, equal size sections, numbered 1 through 7. Okay, first question, what is the probability of getting a tail on the coin and a 4 on the spinner? Well, all you have to do is multiply. So we have to find the probability of getting a tail and multiply it by the probability of getting a 4. It's that simple. They're independent, so multiply away. So what's the probability you get a tail on a coin? Well, that's 1/2. I hope everybody knows that. What's the probability of getting a 4 on the spinner? Well, remember that spinner has 7 sections. 1 of them has a 4 out of 7. Get a lot of kids that will say 4 out of 7. No. I want to get a 4, but again, it's a spinner, right? It's got, I'm not going to do a good job here, but it's got 7 equal size sections. 1 of them is labeled 4, so 1 out of the 7 sections is a 4. So the probability of the probability of spinning a 4 is 1 out of 7. So multiply, 1 times 1 is 1, 2 times 7 is 14, and boom, you got your probability. More than welcome to make it a decimal if you want, 0.071, but fractions are totally fine too. How easy was that? All right, let's try another one. What is the probability you get a tail on the coin and an even number on the spinner? Okay, so I need to get a tail and an even number, but there's multiple even numbers. There's a 2, there's a 4, and there's a 6. So I got to consider 3 scenarios. I could get a tail, and then I can get a 2, or I could get a tail, and then I could get a 4, or I could get a tail and then I can get a 6. So the probability of getting a tail is 1/2. The probability of getting a 2 is 1/7. Okay, that was easy. The probability of getting a tail is 1/2. The probability of getting a 4 is 1/7. The probability of getting a tail is 1/2. The probability of getting a 6 is 1/7. So the probabilities are all equal, right? The probabilities are all 1 out of 14. But what they represent is actually different. The first on the far left is a tail and a 2. Then a tail and a 4. And then a tail and a 6. But they all equal 1/14. But they are technically different outcomes when you say it out loud in terms of what it represents. Now, notice what I said. I said any one of these could happen, and it will satisfy what I'm looking for, tail and then an even number. So I can get a tail and a 2, or means add, a tail and a 4, or a tail and a 6. Now, do I have to worry about subtracting any overlap? No, there is no overlap. You can't overlap tail with even. Those are mutually exclusive events, right? Because you can't have a tail. It can't be at the same time. It's a tail. Okay, you get my point. So essentially what I'm going to do is I'm going to take 1/14 plus 1/14 plus 1/14, because any one of these three outcomes represents a tail and an even number. So add those together and we get 3/14. Very nice when you have a common denominator already. So 3/14. Pretty easy, but again, that was a good example because it also incorporated adding, because what I was looking for had 3 distinctly different possibilities. All right, let's look at non-independent events now. And I don't want this to stress you out because it's very easy. So a small bag contains 20 marbles, 10 blue, 6 green, 4 red. You reach and randomly select out 2 marbles. So I'm going to reach in, select out a marble, reach in, select out a second marble. Now I want 2 marbles when I'm done, so I'm not putting that first one back. That's what makes this non-independent. Because what happens on the second selection is definitely impacted by what happens on the first. And as long as I consider that, it's actually not that difficult. Follow with me here. All right, what is the probability you reach in and get 2 blue marbles? So I want to get a blue marble on the first, and then I want to get a blue marble on the second. But I just got to be careful because the probability of what happens second changes. And it's very simple. Don't stress about this. All right, reach in. What's the probability I reach in and I get a blue marble on that very first selection? Well, there's 10 blue marbles out of 20, so that's 10 out of 20, 1/2. Okay. But this is where we have to think non-independently here. We got to use our brains. We got to think conditionally. I selected a blue marble, which means when I go back in for that second marble, there's only 9 blue left out of 19 total marbles. So this right here is technically a conditional probability. It's the probability of getting a blue marble given you already got a blue marble. That's why the numerator changes to 9, because there's only 9 blue marbles left. The denominator changes to 19 because there's only 19 marbles left in the jar. So that's it. That's how simple it is. You just have to use your brain and understand that if I'm not putting that first blue marble back, well, what happens second changes. All right, so 10 times 9 is 90. 20 times 19, I'm actually grabbing my calculator because I don't know that off the top of my head, is 380. So there is your answer. Obviously, you could reduce that. Obviously, you could divide that out to get a decimal, 0.237. Easy. Okay, next question. What is the probability you reach in and pull out a blue and a red marble? Okay, so this is where we really have to think. I want to find a blue and a red. So I'm going to reach in, pull out a marble, reach in, pull out a marble, and at the end, I want 1 blue and I want 1 red. Well, this is where we really have to open our minds to understand what's happening here. Because there's 2 possibilities. I could get the blue first, then the red, or I could get the red first and then the blue. So let's walk through it. All right, blue first. Well, I reach in, there's 10 blue marbles out of 20. Okay, now I need a red one. Well, I pulled out a blue one. That still means there's 4 red left out of 19. Okay, I still took a marble out, so that 4 was, there's 4 red, but I took a marble out, so there's only 19 left. Or I could get the red one first. That would be 4 out of 20. I reach in, there's 4 red out of 20 total, and then I need a blue. Well, okay, I got a red one, but there's 10 blue still in the bag out of 19 total marbles. Now listen, when we multiply these out, we get 40 out of 20 times 19 is 380. So both of them have the same probabilities. This is kind of what we saw in the last problem. They both have the same probability, 40 out of 380. But when you say them out loud, they are technically different, right? One is blue, then red. One is red, then blue. So I would basically have to add, because either one of these will make me happy. They can't both happen at the same time, right? They're two separate things, blue first, then red, or red first, then blue. So I just have to add these two probabilities together. 40 out of 380 plus 40 out of 380 is 80 out of 380. It's really that simple. Now, one more way you could do this problem. Some kids like this. I hope what I just explained made sense, but some kids like to do what's called a tree diagram. So they say, okay, what could happen with that first selection? The first marble could be blue, 10 out of 20. The first marble could be red, 4 out of 20. Or the first marble could be green, 6 out of 20. Then we say, well, what could happen with that second marble? Well, the second marble could be blue, second marble could be red, second marble could be green. Well, if the first one's blue, right? So tree diagrams show conditional probability. If the first one's blue, there are 9 out of 19 blue left. There are 6 out of 19 red, and, well, excuse me, that was 4 out of 19. 6 out of 19 green. So the 19 is there because I took out one marble, right? So there's only 19 left. But if the first one was blue, well, there's only 9 blue. And the same thing, if the first one was red, again, I'm going to think, well, then I could have a blue, I could have a red, I could have a green. If the first one's red, the second one being blue is 10 out of 20. Red would be 10 out of 19, I'm so sorry. 3 out of 19 for that second red. And then green would be 6 out of 19. And then again, if that first one was green, I could get blue, red, green. Blue would be 10 out of 19. Red would be 4 out of 19. And then a second green would be 5 out of 19. So if you're saying, all right, well, what do I want? Well, I want a blue and a red. So we could get blue, then red, or red, then blue. So those were our two outcomes. So we have 10 out of 20 times 4 out of 19. That's 40 out of 380. Or we have red, then blue. That's also 40 out of 380. So two of these outcomes are going to make me happy in terms of I got a blue and a red marble at the end. So we add those two together, and that's how we get 80 out of 380. So sometimes tree diagrams are really nice. It helps kids really kind of follow through what could happen. All right. Now let's talk about events that are, well, let me fix this. Kind of a little bit more. Okay. They're non-independent events, but they really are independent. Well, typo there too. Man, I'm terrible today. Okay. Here's the deal with this. Now, why am I saying that they're non-independent, but they're really independent? All right. This is where you really need to pay attention for a hot second. All right. You're at a factory that makes thousands of marbles. Thousands. Maybe even hundreds of thousands. Tons of marbles. They make tons of marbles. Now, they say that 24% of all marbles they sell and they make are blue. Okay, great. You select 2 marbles from the huge batch of marbles. Okay. What is the probability that they are both blue? Well, I need the first one to be blue. Okay, well, it says 24% of our marbles are blue, so what's probably the first one's blue? 24%. Now, listen. If I take out a blue marble, I have technically changed what's left. Now, in the previous problem, there was only 20 marbles. If I take out one, there's 9 blue left, 19 left in the whole bag. I mean, that's a significant change, right? Like I have literally changed what happens next. But if you're at the factory and there's hundreds of thousands of marbles, if you take out one blue one, do you really think that you have changed the probability of getting a blue one again? It's probably still going to be 0.24. Now, I will be honest, like let's get down to the basement here, okay? Technically, if there's thousands and thousands of marbles and you take a blue one out, well, there's technically one less marble. So the probability that the next one is blue might be 0.23999999999999999. So at that point, we're like, well, what's the difference? We might as well just say it's 24%. So this is why I'm saying that these are independent events, even though they're not really independent. Because the idea is that there's so many marbles that if you take one away, it doesn't really matter that much. Whereas that small bag, it did matter. But when you got thousands, it doesn't matter. So if you're trying to find the probability of 2 blue, You just take 0.24 for the first blue, 0.24 for the second blue, multiply that together. Maybe you do 0.24 squared if you're looking to be a little faster, 0.0576. Okay, now technically the probability of this second one being blue does change, but it just doesn't change enough for us to care because there are so many marbles. Now, it's important that we understand that there's actually an explanation for this. It's actually called the 10% rule. The 10% rule says this: when we select without replacement, right, we're not putting that first marble back. If the amount that you select out of the population is less than or equal to 10% of that population, then independence can be assumed. Meaning it's just not that big of a deal. So that's kind of what this rule says, right? You don't really, most of the times you don't actually measure what the 10% is. You just have to have an understanding that if there's thousands and thousands of marbles and I take out 2, that's clearly less than 10% of all the marbles. I mean, even if there was 5,000 marbles, 2 divided by 5,000 is literally 0.0004. It's just a very small chunk. It's not that big of a deal. So the 10% condition, which this is a really important rule to know, we're going to talk about a lot the rest of the year, is basically saying, hey, listen, if you take only a small fraction out, you're allowed to assume independence. Even if it's probably not really independent, you could still assume it because you're not going to make a major change to what happens next. And this example really shows that. Because, again, maybe the probability for the second marble being blue is 0.23999999999999. Does it really matter at that point? Okay, let's do the second question here. What is the probability that one is blue and one is not blue? But again, now this matters, right? The first one could be blue. The second one could be not blue. I'll put not blue. Or the first one could be not blue, and the second one could be blue. So we do have to walk through that there are 2 different ways this can happen. So first one is blue is 24%. What's the probability that the second one is not blue? Well, that's called the complement. There's a 24% chance it's blue. There's a 76% chance it's not blue. And then or I could have a not blue first, 76% chance not blue, and then a blue second. Now again, multiply these out, 0.24 times 0.76, it's 0.1824 either way. Both of these are 0.1824. But they are technically different. Even though the probabilities are the same, the actual explanation, blue first, not blue second, not blue first, blue second, that is different. So that's why it matters. So we would simply add these 2 probabilities together, and we get 0.3648. So really taking the time to process what you're doing is probably the most important thing here. All right, so make sure that we truly understand that 10% rule. So let's do a couple more problems here, kind of just making sure you believe me on this 10% rule. All right, the probability that a randomly selected person is left-handed is 13%. You select 4 people. Okay, here's the 10% rule. If you select 4 people, there's millions of people. Even if we just say from Ohio, there's millions of people in Ohio. Do you really think selecting 4 people out, even if all 4 of them, unbelievably crazy, were all left-handed, do you think that really matters? Like, is you taking 4 people away going to make that 13% go down to like 7%? No, it might drop to 12.999999999999999%. But at that point, what does it matter, right? So this is where this allows us to maybe not be independent, but because we're taking such a small fraction of the population away, people, I'm pretty sure we're fine. All right, so what's the probability that all 4 people are left-handed? Well, that would be 0.13 to the 4th. Let's use exponents to make this faster, guys. Come on, right? I need a lefty, a lefty, a lefty, a lefty. 0.13, 0.13, 0.13, 0.13. So 0.13 raised to the 4th would be, be careful when you look on your calculator. It is scientific notation. Hopefully you're doing this with me. You got to move the decimal 4 times to the left. It'd be 0.000286. So again, very, very, very unlikely. That would, if you move the decimal back 2 times, that'd be 0.0286%. Oh my gosh. So very unlikely that you're going to get 4 lefties if you just grab 4 random people. All right, what's the probability that all 4 are not lefties? Well, come on, complement rule. If 13% of people are left-handed, 87% are not. So I need not lefty, not lefty, not lefty, not lefty, 0.87, 0.87, 0.87, 0.7. So 0.87 to the 4th. And that is 0.573. Very likely. 0.573. In fact, that is very, very likely because most people aren't left-handed. So it would be totally normal if you got 4 non-lefties, right? Okay, next question is going to take a little bit more thinking. What is the probability that only 1 is left-handed? Now, this is where we really got to take our time because this could happen 4 different ways because order matters. The first person can be my lefty, then non, non, non. Or my second person could be my lefty. So that's non, lefty, non, non. Or the third person, non, non, lefty, non. Or the last person, non, 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 lefty. So there are 4 different ways that one person could be left-handed out of 4. So I'm going to add these options together because any one of them is going to satisfy what I'm looking for. So now here's the important thing. The probabilities are all the same. All 4 of these situations have a lefty person, maybe you could put a 1 there, 1 lefty person, and 3 persons that are not. And the order you multiply doesn't matter. So 0.13 times 0.87 times 0.87 is the same as 0.87 times 0.13 times 0.87 times 0.87, right? And I can keep going. So the point is that all 4 of these options have 1 left-handed person, which is a 13% probability, and 3 non-lefties, an 87% probability. But there are 4 distinct different ways it can happen. So basically, I'm going to multiply that by 4 because remember, multiplication is repeated addition. So taking the same number 4 times. So 0.13 raised to the first times 0.87 raised to the third. And then I'm going to multiply that by 4 because there's 4 options, right? It would be the same thing of me adding it 4 times. Why not just multiply it by 4? And I get 0.3424. 0.3424. So again, very likely, it's actually very likely, not that weird at all, if you grabbed 4 people randomly off the streets and one of them was a left-handed. The probability would be 34.24%. But again, it's truly important that you understand what I was doing there. 4 options, but they all have the same math. They all have the same probability, but they are 4 distinctly different options. All right. Now, the only other thing we got to really watch out for is conditional probabilities. When you read a problem and it contains multiple conditional probabilities, often a tree diagram really helps. So real quick, what are some conditional probabilities? What are some conditional statements? Well, for example, given that a car breaks down, the probability it is because of an electrical issue is 0.08. That is a conditional sentence because it had that given, right? So we're finding the probability that there's an electrical issue, given the car broke down. So the car had to broke down first for there to be that electrical issue. That's a conditional probability. Got to make sure you understand that when you read. Or another example is given a car breaks down, the probability is because of an engine issue is 26%. So again, we're finding the probability that there's an engine issue, but given the car broke down. A third example is if a family's first child is a boy, the probability the second is a girl is 65%. So again, we're finding the probability that the second child is a girl, but it said given that the first was a boy. And for some reason, I don't know why, apparently having a boy first makes you more likely to have a girl second. I don't think that's really true, but hey, you never know for a particular family. But again, you got to recognize when you read conditional sentences. All right, let's do a problem here that definitely has a conditional sentence to it. And I'm going to show you how a tree diagram really makes this cool and simple to understand. All right, a racehorse is entered into 2 races. The probability that the horse wins the first race is 30%. Okay, that's not conditional. It just says the probability the horse wins the first race is 30%, which should automatically tell you the complement. Probability it loses the first race, 70%. Oh, but here comes a conditional sentence. If the horse wins the first, the probability the horse wins the second race is 45%. So to get that 45% chance of winning the second race, the horse has to win the first. So that's a conditional sentence. If the horse loses the first race, the probability it wins the second is 10%. So once again, to have that 10% chance of winning the second race, the horse had to lose the first. Now this is where a tree diagram really, really helps. So let's talk about that first race. The horse could win that first race, or the horse could lose. There is a 30% chance it wins the first race. We were told that right here. And complement rule tells me automatically 70% chance it loses. Now here comes the conditional. If it wins the first, so I'm going to make a condition off of the first. If it wins the first, there is a probability of 45% that it wins the second, which would actually tell me, again, you got to think about the complement rule, 55% chance it loses the second. All right, then it says if the horse loses the first, now let's make some branches off of losing the first. If it loses the first, there's a 10% chance it wins the second, which means it's got a very likely chance, 90% chance to lose the second. So now I have my four scenarios. The horse could win the first, win the second, lose the first, lose the second, win the first, lose the second, lose the first, win the second. I know that's a lot, but now you can actually see all the probabilities, which makes it really kind of simple. All right, so first question says, what is the probability the horse wins one race? Well, one race. It needs to win one race. That could be win, lose, or lose, win. That would be this branch right here, win, lose, or this branch right here, lose, win. So let's walk through those probabilities, and using the tree is going to make this so simple. All right, win the first, 0.30, lose the second, 0.55. Again, this loss right here was conditioned that you won the first. And based on our tree diagram, the 55% chance that you lose the second if you win the first. Or, means add, lose the first, 70%, win the second, 10%. Once again, this second win, that 10%, came on the condition that you lose the first. So these two outcomes will result in one win. I don't care, I just want one win. So I do have to multiply and add. So 0.3 times 0.55, that's 0.165, plus 0.7 times 0.1 is 0.07. Add those together, and we get 0.235. 0.235. All right, next question is going to really kind of combine a lot of cool stuff for us here. Okay, given that the horse wins the second race, what is the probability the horse wins the first race? Okay, let's write this down because this is conditional. So I'm finding the probability that the horse wins the first race. Wins first race. Given that it won the second. Wins second. So most kids that aren't paying attention will jump and say, well, there's a 30% chance you win the first race. Yeah, but there's a 30% chance you win the first race if I could care less what happens second. But I do care what happens second. The question clearly says, if you win the second, what's the probability you win the first? So this is definitely conditional, which is going to require my conditional formula. But watch how easy this is, guys. Don't stress. All right, remember the conditional formula says on top goes both. Win the first and win the second. Well, that's a very simple branch to follow. Win the first, 30%, and win the second, 45%. That 45% was on the condition that you won the first, easy. 0.3 times 0.45. 0.3 times 0.45 is 0.135. So that's my numerator, 0.135. All right, my denominator is you win the second. Okay. There's two ways you could win the second. You can win the first and win the second, or lose the first and win the second. Because all the condition is winning the second. So there are two distinctly different ways that you can win that second race. So I do have to account for both of them because the denominator only cares about the condition winning the second. So I could win 0.3 times 0.45, or I could lose 0.7 times 0.1. Either way, I'm winning the second race. So again, Now, first, please, a little note of algebra. Don't you dare try to cancel the 0.3s and 0.45s. If you learn anything from pre-calc, you cannot cancel through addition like that. Sorry, you got to do them separate. So I already did the numerator. Let me do the denominator. 0.3 times 0.45 plus 0.7 times 0.1 is 0.205. 0.205. So now I got to divide. 0.135 divided by 0.205 is 0.659. 3 decimals, 0.659. So if you win the second race, there's a very good chance you won the first race. So the probability that you win the first race, given that you won the second, is almost 66%, 0.659, 65.9%. All right, guys, that's it. A lot going on in this video. I'm using a lot of rules in this video, but I'm trying to make it as simple as possible. I don't want you to overthink these problems. You just have to process. You have to walk through them in your brain. Tree diagrams help with that. Understanding independence and what happens second. Does that change because of what happened first? You just got to walk through it all in your brain. And I think if you walk through these problems, don't sprint, walk, I think probability is actually quite easy. All right, see you later. We're going to do a lot of practice in class.